Hello, good people. Welcome to video 3. We're going to test out this second derivative test for relative extrema or local extrema to figure out what is given the information that we have, and sometimes we're given limited information. Can we apply the second derivative test? Okay. Example 1. No equations, only a table of values, right? Function f is twice differentiable. I can take the derivative twice. The derivative exists for first derivative and second derivative, with selected values of f prime, and f double prime given in the table above. So we have x values here. At x equals 1, the f value, the function value is 4, the first derivative value is 3, the second derivative value is negative 6, and so on. Find any relative extrema on the graph of f of x and explain your reasoning. Okay, so why don't we do this? Can we identify critical values? Critical values are where the first derivative is equal to 0. So the first derivative is equal to 0 at x equals 2 and at x equals 7. So my two critical values are x equals 2 and x equals 7. Great. Now we're going to take those critical values and we're going to put them into the second derivative. So f double prime of 2. Well, f double prime of 2 is positive 4. And f double prime of 7. Well, f double prime of 7 is negative 3. So what does this tell us about the behavior of the graph? This tells us that f has, now remember, second derivative is concavity. So if my second derivative is positive, that means it's concave up. That means there's a relative minimum there. F has a relative, I'm going to write the whole word this time. It has a relative, there you go, minimum of, what is the relative minimum? What is the function value, the y value at x equals 2? Well, at x equals 2, the y value is 7, right? So it has a relative minimum of 7 at x equals 2. So the relative minimum is 7 at x equals 2 because f prime of 2 equals 0. In other words, that's a critical value. And f double prime of 2 is 4, which is greater than 0, meaning that's concave up. So maybe I should say by the second derivative test, comma, f prime of 2 is equal to 0, and f double prime of 2 is equal to 4, which is greater than 0. Let's write it that way. So what am I telling the grader? I'm telling the grader that I've answered the question. The question is what is the relative minimums and maximums, right? It didn't say where, it said find any relative min. So they want to know the y function value. So the function value, the lowest point, or a low point, I should say, is relative minimum of 7. Where does it occur? At x equals 2. Now, how do I know that's true? Oh, by the second derivative test. Because f prime of 2 is equal to 0, I know that 2 is a critical value, and the second derivative of 2 is positive 4, and I know that it's concave up. Same reasoning for the next one. F has a relative maximum, and I know this is a relative maximum because the second derivative is negative. If the second derivative is negative, that means it's concave down, and that's going to give me a maximum, right? It helps me to visualize how I'm using the second derivative values, right? By doing it like a little curve that shows the concavity up or down. F has a relative maximum. What is the relative maximum at 7? Well, let's see. At 7, the y value is negative 2. Of negative 2 at x equals 7. And I know this because the first derivative at 7 is equal to 0, so that means it's a critical value, and the second derivative value at 7 is negative 3, and that's less than 0, which means it's negative, and that means it's concave up. Or in this case, concave down. My bad. So this is a critical value, and I know that the second derivative is negative, and therefore it's concave down. And by the second derivative test, we are guaranteed that this is going to be a relative maximum. So I'm going to zoom out so that you can see the whole setup there, and we can find out that the second derivative test can help me find relative minimums and maximums a lot quicker, right? Just by knowing the pieces of information, I can figure that out. What about, let me leave it here, or maybe you can pause it if you need to more time to fill in what we just found. But again, we're using the second derivative test for relative extrema, find critical values, check those critical values in the second derivative to determine the concavity, because if it's the second derivative is negative, then the function is concave down. I know that I have a relative maximum, and conversely with relative minimums. Okay, we'll do one more and then we'll pause. Example 2, the function f, the function f is twice differentiable for all real numbers of x and has exactly two critical values. Selected values for f prime, the derivative of f, are shown in the table above, along with the graph of f double prime, which is the second derivative of f. At which values of x does f of x have a critical point? Well, this means I need to know where f prime is equal to 0 or undefined. And that happens at x equals -3 and x equals +3. So where's the first derivative equal to 0? Oh, at x equals -3. The first derivative is equal to 0. Oh, at +3. I found my critical values. Yes. For each point, determine if f has a local extrema, a local minimum or a local maximum at the given x value, or state that it cannot be determined. All right, well, let's find the second derivative. Let's find the second derivative at -3, and we'll find the second derivative at +3. At -3, the second derivative, well, this is the second derivative graph. So the y values of this graph are the second derivative values. So when x equals -3, I don't know what it is, but I know that it's positive. So therefore, the second derivative at -3 is greater than 0. It's positive. By the second derivative test, since f prime at -3 is equal to 0, because it's a critical point, and f double prime at -3 is greater than 0, that means the concavity is opening up. There is a relative minimum of f at x equals -3. What is that relative minimum? I don't know. By the way, I guess since they use the word local, I shouldn't use the word relative. I should use the language that they use. So let me try to erase this, which I can't apparently. And then let me write. Is a local minimum of f. There is a local minimum of the function f at x equals -3. That's it. Okay, so let's look at the second derivative at +3. The second derivative of +3 is where the graph, where is the graph at +3? Well, the graph of +3 is at 0. Uh-oh. By the second derivative test, since f double prime of 3 is equal to 0, we cannot determine the local extrema. Notice the phrasing is not, there is no local extrema. I just can't use the local, I can't determine the local extrema because I don't have enough information, the second derivative is equal to zero, that test falls apart, right? Questions about that? If you do, bring them to class and we'll discuss them. These first two examples using tables and graphs, not equations, which could be a sign that I might have to use or I could use and save time by using the second derivative test for relative extrema.